Swayam Prabha. Digital India. Educated India.
We were discussing in the last lecture about transmission electron microscopy, and if you could recall, we were discussing about the specimen preparation techniques, and we have discussed about one of the methods where it involved fixation, embedding and sectioning and finally staining, and to view the samples in electron microscopy. Now, other than that conventional methods, there are other methods of contrast creation for electron microscopy. Let us little bit discuss about some of those methods. Now, one is negative staining. Now, negative staining is used for observation of samples containing small particulate material such as subcellular fractions, viruses and some macro and protein complexes. Now, here specimen is applied to a grid covered with a support film and is surrounded by an electron dense substance, so that particles in the sample appear electron lucent. Now, the stains used most frequently are 1 to 2% solutions of uranyl acetate or phosphotungstic acid, ammonium molybdate, methylamine tungstate and uranyl formate. Now, the sample suspension, which is 3 to 5 microliter, is placed on the grid, that is foam wire carbon coated grids, and they are made up of hydrophilic by glow discharge shortly before applying the sample. So, what you have is that particles adhere to the film and the edge of the grid is then touched with a piece of filter paper to soak remainder of the suspension by capillary action. 3 to 5 microliter of negative stain is applied for some time, and after drawing off the stain solution, grid is dried and it immediately observed in transmission electron microscopy. Let me show you this on the screen and give you a feeling about how this whole thing happens actually. All right. So, the negative staining, like I said, you are not really staining the specimen or the particulate matter, which could be anything, rather you are surrounding it with the stain, and the stain gets into the crevices and crafts which are present in here. So, what you have is you have like electron rich area surrounding, but the object or specimen is electron translucent. So, what you have is essentially you will see here that if you have a particular area so, what you have is if your material is put in here, then this material is surrounded by a particular stain here. Now, this stain will get into the surface crevices and other imperfections, and that will give you a contrast and will give you finally an image, and this could be dried off later on, extra thing could be dried off. So, this one method is very good, it gives a good contrast and could provide you with images for certain specimens. So, it is not applicable for a lot of different applications, but it is used for observations of samples containing particulate materials or subcellular fractions. Now, another method is metal shadowing. Now, metal shadowing is another widely used technique to increase the contrast of certain specimen by depositing thin coat of metal onto the surface and cast shadows. What does that mean, casting shadows? We will just try to make you understand this. Now, this whole thing is performed in a vacuum evaporator containing one or more pairs of electrodes, and it is connected to a dual pumping system, which is rotary and oil diffusion pumps. Now, the metal to be evaporated is held between a pair of electrodes and heated by electric current. So, this whole thing is done at an angle of 45 degree or less. So, your metal is placed around 45 degree or less to the samples actually. Now, metal which could be platinum or sometimes tungsten together with carbon is deposited on surfaces which are facing the filament, that is which are towards filament side, while opposite surfaces in a specimen and grid will remain uncoated and incapable of scattering electrons. So, what you have is the sides which are coated will scatter electrons and will not be seen in the fluorescent screen, and sides which are not coated, that is shadows, will be passed, electrons will be passed from there and the fluorescent screen will be lighted up there. Now, the areas in shadow appear bright on viewing screen, while metal coated areas will appear dark. Now, technique provides an excellent contrast for isolated materials and produce a three-dimensional effect. In many metal shadowing technique, there is another technique which could be used, which is rotary metal shadowing. Now, in this rotary metal shadowing, thin film of metal is deposited on a specimen at a very low angles. Like if you could see in metal shadowing, it was 45 degree or less. Here 8 to 10 degree, at 8 to 10 degree metal is deposited, while the sample is being rotated. Now, metal atoms deposit on structures projecting above the specimen surface, and so they will be coated. So, molecular size, shapes and interactions can be determined by use of this technique. It is purified samples of nucleic acids, proteins, protein interacting with nucleic acids, etcetera, can be seen in here on appropriate substrate. So, let us see how this in this figure. If you see, this is for negative staining, what I have already showed to you, that there is object, there is a stain and there is a supporting film. For metal shadowing, which I was trying to explain, it is being done in a evacuated chamber, and what is essentially is done is that you have a metal which is being heated and evaporated, and there is a sample with different ups and downs or different surface structures. So, when you are depositing this metal at an angle, then only the exposed parts or the parts which are facing the metal will be coated, and rest of part you can see are not coated. So, these will be seen bright on the screen, and these will be seen dark on the screen. You can see here the arrangement as such that the filament is held between two electrodes, and it is at an angle, and you will get a three-dimensional effect of the images. In rotary metal shadowing, this angle will be 8 to 10 degrees, and only the surface things which are projecting outside will be coated in here, and that particular outer surface view could be seen. So, this was another technique which was metal shadowing. So, we have seen negative staining and metal shadowing. These are other two techniques which could be utilized for creating contrast. Now, other than that, there are cryo techniques. Cryo techniques means which are done in very cold conditions. Now, here specimen preparation procedures are employing ultra cold conditions or temperatures are used. Now, this could be liquid nitrogen to liquid helium temperature, that is minus 196 degree Celsius to minus 271 degree Celsius in place of chemical fixation. Now, if you remember, in chemical fixation, you are doing chemical fixation, dehydration and all those things which are not done in here directly. Now, main goal is to retain the native structure and properties of specimen. So, let us see certain steps of cryo techniques. One is cryo fixation. Now, in cryo fixation, you have to rapidly freeze the sample to preserve biological details actually, and this is done. This is very critical aspect, because you would like to avoid the formation of ice crystals during freezing, and if ice crystals forms, they can disrupt cellular membranes and other structures. So, freezing rates are very high and you avoid formation of crystals. Now, cryogenic liquids such as liquid propane, ethane or freon having large differences in freezing and boiling points can be used here. The specimen needs to be plunged rapidly and deeply into a cryogen. So, one way is to use slam freezing devices. The slam freezing devices employs a solenoid driven plunger to which sample is attached and is rapidly slammed against a polished copper surface cooled to liquid nitrogen or liquid helium temperature. So, slam freezing is one way to freeze rapidly the sample. Now, freeze substitution is done where frozen samples are placed in acetone or methanol at -85 degrees Celsius for several days. Now, what it does? It slowly brings it dehydrates the sample by substituting frozen water by particular sample like acetone or methanol. Now, then again you can go to fixatives like osmium tetroxide, glutaraldehyde or paraformaldehyde can be used for fixation. Staining solutions like uranyl acetate can be added to solvent, and at room temperatures samples can be embedded in epoxy resins or in low temperature resins. The sectioning is done in cryo conditions. So, it is called cryo sectioning. Thin areas, thin sections of cryo fixed samples can be prepared using a cryo ultra microtome. So, you have to see that microtome, if it is placed in the cold conditions, it is called cryo ultra microtome. So, this was about little bit about cryo techniques. One of the cryo techniques which is widely used is the freeze fracture technique. Now, this technique is very important and it provides unique view of cellular membranes and distribution of integral proteins in the membrane, and specimens here are usually fixed in glutaraldehyde and cryoprotected with 20 to 30% of glycerol before freezing. So, what is done is, like if you are preparing a sample for freeze fracture, the first thing you have to do is that you have to fix the specimen to preserve the internal details by a fixatives called which is could be glutaraldehyde, and also you have to cryoprotect so that crystal formation could be avoided by say 20 to 30% glycerol before freezing. Once cryoprotected, then these samples are rapidly frozen and then they are transferred to a special stage in a vacuum evaporator. Now, this is modified version which could include a fracturing device. Now, fracturing device is required, like we are saying the membranes could be fractured at the middle, and there is a scalpel or razor is mounted in these devices. Now, fracture plane as we call it usually takes the path of least resistance through the frozen block sample, that is whichever path will give least resistance or impart least resistance, that part of fracture this path of fracture will be followed. Now, fracturing is usually done at -100 degree Celsius, and the fractured surface is immediately shadowed with platinum and carbon at an angle of 45 degree, creating a replica of surface, then with the carbon alone at an angle of 90 degree to reinforce the replica. Now, a specimen is thawed and the replica is placed on foam wire coated grid specimen grid. Then grid will be viewed in the electron beam. The variation in thickness of the metal in different parts of the replica produces necessary contrast in this image. So, there is another addition extension of this particular technique, which is it could be more informative by a simple step called freeze etching. Now, in freeze etching what is done is that the frozen fractured samples in cold chamber is exposed to a vacuum at an elevated temperature. for a very small period of time. Now, what happens is during which a layer of ice gets evaporated from the surface, and once water has been removed, the surface of the structure can be coated with heavy metal. So, more information is exposed in here due to the water evaporation. So, if you see in this figure clearly explains the freeze fracture technique. So, if you see here, the specimen is here, there is a specimen support and there is a specimen. This specimen, after cryoprotection through fixation and cryoprotectant solvent like glycerol, this will be rapidly frozen, and after rapidly freezing the sample, it will be put into this chamber, which is cryo chamber or cold chamber. Now, if you can see here, there is a scalpel or cold knife in here, and this cold knife is utilized to create the fracture. And like I said, fracture will take path of least resistance. So, in membranes, this is the path of least resistance it will take, and it will be after the fracture, you will see that you will get the two membrane or two monolayers separated in the membrane bilayer, and but integral proteins are present in there. Now, after this you will shadow it with the platinum or other metals, and at 45 degree, and then again at 90 degree with carbon. So, what will happen is a replica is formed. You can see here a replica which is formed, and this replica could be utilized for to be used under the electron microscope. Rest of the things could be discarded. So, since replica has all different information as per the surface structure of the integral proteins and other things here, that could be used for imaging in the electron microscope. So, freeze fracture technique is one of the very important techniques used in transmission electron microscope. So, this was about the scanning electron microscope. Now, let us move on to the this was about the transmission electron microscope. Now, let us move on to the next electron microscopy technique, that is scanning electron microscopy. Now, electron microscopy, in contrast to transmission electron microscopy, will be utilized for surface viewing or surface details. So, scanning electron microscopy is a type of technique that produces the image of a specimen by scanning it with a focused beam of electrons across a rectangular area of the specimen or in a raster scan pattern. Now, when electron beam interacts with the specimen, either emission of low energy or secondary electrons or backscattered high energy electrons will provide signals carrying information about the specimen surface topography and composition. Now, SWAYM has provided the means to examine in great clarity and detail the surface of objects ranging in size from a virus to an animal head. So, you have variety of specimens could be used in here. The construction and operation of SWAYM are very different from TEM, that is transmission electron microscopy. Let us see how this is different from TEM, and we will be seeing the optics of this later on in a little while. Now, illumination system here, though basic things are same, but there are noticeable differences. One is that the cathode is maintained at a negative potential difference to anode around 2 to 30 kilovolt rather than 10 to 100 kilovolt. So, that is one difference. Then there are 3 condenser lenses are used in SWAYM, and the specimen is not placed, rather a specimen is placed at the bottom rather than in the middle of the column. Now, third condenser lens is used to reduce further the size of the beam or probe, which is around 5 nanometer in diameter, and as this lens is used to focus beam on a specimen and thus focus image, it is often called as the objective lens. So, there is nothing like projector lens here, you can call it projector lens or objective lens. Size of the beam spot or probe is a major determinant of resolution in the scanning electron microscope. With a small probe, the volume of specimen with which the beam of electrons interact to give rise to secondary electrons is smaller. Thus, the signal for each individual picture element making up the final image originates from a smaller part of specimen. Also, deflection coils are used to shift and tilt the beam during operation and alignment. So, deflection coils in final condenser lens are used to raster the beam over the surface of the specimen, and the size of the area covered by raster pattern is inversely proportional to the magnification of the image. We will see how. Likewise, the specimen stage or specimen carrier is quite different from the transmission electron microscopy. Now, in the stage of scanning electron microscope, it is designed to accept a wide range of specimen sizes up to say 100 millimeter or more in diameter. So, you have to have much versatile specimen stage as compared to transmission electron microscope. Now, this has a large motion which may go up to 50 millimeter or more in x y direction, and it can rotate a full 360 degree. The specimen stage can tilt up to 90 degree, and in addition to changing the angle of view, tilting and rotating the specimen relative to electron detectors may help to enhance the signal. So, you can manipulate it in various ways. Other important part is that stage can be raised or lowered also, that is you can it is called Z adjustment, you can lower or raise the stage to accommodate large or small specimens. The working distance or the focal length of final lens is varied in order to focus the electron beam on the surface of the specimen. Now, long working lengths increase field depths, but decrease resolution and signal strength. So, that has to be taken into account. Imaging system here in SEM is based either on secondary electrons. Remember, here it is not transmitted electrons, rather it is backscattered electrons. So, imaging system will be based on either secondary electrons which are generated by inelastic scattering events near the surface of the specimen, or on primary electrons which are of beam that are reflected or backscattered from the specimen. So, you would have two kinds of image formation methods. One is on the basis of primary backscattered electrons, another on generation of secondary electrons or inelastic scattering. Now, we will discuss here one of the detectors based on secondary electron detectors. Now, this here in this particular detector, electron beam is focused by electromagnetic lenses to a small spot and is rastered over the specimen surface. Now, secondary electrons generated during the interaction of the beam and the specimen are collected by detector. The amplitude which is the amplified signal from detector is displayed as brightness on cathode ray tube, and it's which is being scanned in parallel with the beam. So, the magnification of the will be determined by the ratio of diameter on cathode ray tube to the ratio of diameter on the specimen. All right. So, secondary electron detectors which are in common use, one is based on Everhard-Thornley design. Now, in these detectors, a positively charged collector which is around 220 volt attracts the low energy which is less than 50 electron volt secondary electrons, which are then accelerated towards scintillator by a potential of 10 to 12 kilovolt. Now, the photons generated by the electrons striking the scintillator then enter a photomultiplier through a light guide. Now, where they are converted into photoelectrons and their number enhances almost by 10 raised to the power 5 to 10 raised to the power 6 times, and the resulting signal is displayed as brightness on cathode ray tube. Backscattered electrons have higher energies and directed mainly upward in direction of final lens, and they are collected, they will not be collected by the secondary electron detector. So, if you have to use backscattered electrons, then annular backscattered electron detector of a solid state type or a scintillation photomultiplier type are placed just below the final lens. So, that way you can use. Image observation is done by signal from the secondary or backscattered electrons, and which is displayed as an image on a cathode ray tube, or a video monitor which is scanned in parallel with the electron beam scanning the specimen. For photography, the beam is scanned very slowly over the specimen in order to generate a strong signal, and image is recorded on a second high resolution CRT or cathode ray tube. Digital imaging is now a standard feature, and high resolution video printers of laser printers can be used, and it could be kept on a magnetic or optical media, or can be recorded on a magnetic or optical media for computer processing and analysis. So, this was about the image observation. Now, let us see the optics of, like we will discuss this, let us try to understand through this figure. So, like I said earlier, we have shown you electron gun, but only difference is that it is 2 to 30 kilovolt, anode is at a negative potential than anode. So, there is a difference here from transmission electron microscope. Now, if you can see here, rather than having a specimen at somewhere in between, the specimen is placed at the end of the column, and there are two condenser lenses here. There is a scanning coil which scans the beam in parallel on cathode ray tube, and there is a final lens, or we call it objective lens. Now, this specimen area could be tilted, this could be tilted at a certain angle towards the detector. So, secondary detector is placed somewhere here. Now, this detector, which is secondary electron detector, collects the secondary electrons which are of very low energy, and when it collects low energy electrons, they needs to be amplified to see the signal. So, it goes through amplifier and through a photomultiplier tube finally to the cathode ray tube. The ratio of this D to D on a specimen place is gives you the magnification. Now, let us see what is, how does the detector looks like here. If you see in this figure, this is the specimen which is tilted. Like I said, the specimen stage could be tilted here manifold in terms of 360 degree rotation, 90 degree tilting, or move in xy direction or in z direction. There are this is a versatile stage for accommodating various kinds of specimens, big and small. So, specimen is here little tilted, electron beam is coming from the top and it is scanning. Now, this is a coated surface. So, there is a conductive surface it becomes, and so secondary electrons generated here will be focused or collected by a collector which is at a positive potential of around 50 to 300 volt. Now, this collector attracts the electron and then they are passed into the scintillator which is at positive potential of 10 to 12 kilovolt. Now, these scintillators converts them into photons, and these photons will be then entering a photomultiplier through a light guide. This is a light guide here. Now, in photomultiplier, photons will be converted to the photoelectrons, and then through different diodes and anodes, and there is a photocathode here and anodes, they will be directed towards the anode, and these photoelectrons through these system will be amplified many fold, so that the signal can be clearly seen on the cathode ray tube. So, this is how the secondary electron detector works. All right. So, this was about the optics of scanning electron microscope, and one of the detectors we have discussed, that is secondary electron detector. Now, the main part of this whole microscopy technique is that what you are viewing is the surface details. Now, how to preserve those surface details while processing or making the specimen for the microscopy observation. So, in SEM, a 3D view of biological specimen which could be cells in culture or any other biological specimen for that matter, will be imaged. Now, therefore, special preparative procedures are needed to preserve surface details of the specimen and make them visible. Let us see how this is done. Now, specimen must be dehydrated before placing them in the instrument, as we have told you earlier, because of the high vacuum conditions. But if you dehydrate the specimen, then surface details will be lost because of the surface tension problems. So, what happens that normal procedures where air drying or alcohol dehydration followed by evaporation of solvent is employed, it will produce surface tension forces that will distort the cell shapes and disrupt delicate membrane structures. Now, the effects of surface tension can be avoided. So, you have to make sure that surface details are not lost, and that is what you are trying to view. So, how to do that? We have to avoid the effects of surface tension, and this could be done by using one of the methods called critical point drying method. Now, what is this critical point drying method? Now, when a solvent is in equilibrium with its vapor phase, is heated to a critical temperature and subjected to its critical pressure, that is we call critical point, the densities of liquid and vapor phase are equal, and therefore, the phase boundaries disappears. And when the phase boundaries disappears, the transition from one phase, that is from liquid phase to vapor phase, is done without any problems of surface tension, that you are not developing a surface tension. Now, if the temperature is held little above critical temperature, the vapor can be exhausted without condensation and specimen is dried. So, what you are trying to do is here that you are trying to preserve the surface details by critical point drying, and but how to do that actually? Which particular solvent needs to be used? Now, here for critical point drying, liquid carbon dioxide is the commonly used solvent here for critical point drying. Why? Because its critical temperature is 31 degrees Celsius and its critical pressure is 1080 psi. Now, this is readily achievable without the risk of damage to the delicate biological samples. Now, compare it with the water. The critical temperature and pressure of water are 374 degrees Celsius and around 3184 psi, which cannot be used with biological samples. So, the liquid carbon dioxide is used where first the samples are exchanged, the water is exchanged for liquid carbon dioxide, and then at critical point they will be dried to avoid surface tension problems to preserve the surface details. After drying, surface of specimen will be made conductive in order to dissipate the charge that build up as electron beam is scanned over specimen. So, specimen first part of the specimen preparation was critical point drying, and so once you have dried it and you have preserved all different details, you have to coat it with the metal, heavy metals. Now, for most applications in which surface topographic information is sought and low to moderate magnification is required, the surface is coated with a metal such as gold in a sputter coater. For higher magnification, gold, palladium alloy and other metals like platinum, chromium etc., are used, which have a smaller grain size. Now, gold has a grain size of from 50 to 40 nanometer, which is little higher, which is little more and could not be used for higher magnification. Now, tungsten and tantalum with fine grain size can be deposited in thin layers for much higher magnification. Now, here you will use again a vacuum evaporator equipped with rotating and tilting stage for doing this. Let us see how it is done. So, if the specimen will be used for backscattered electrons imaging, of gold labeled antibodies could be utilized and it could be made conductive. Now, let us see how this is sputter coater is utilized for coating the specimen. So, what is done is that specimen is mounted on aluminum stub with conductive tape and is placed in a sputter coater. The chamber is evacuated and the argon gas is introduced to maintain a pressure of about 6 to 7 pascals. The sputter coater has a ring shaped cathode or target made of metal to be sputtered and a ring shaped anode between the cathode and specimen. Application of high voltage generates a plasma of ionized argon and positively charged ions bombard the target, knocking out metal atoms which are scattered in all directions as they collide with argon ions and electrons, and the all surface of specimen are evenly coated by multidirectional metal atoms. Now, heat damage to specimen could be avoided by cooling the specimen using a magnet to deflect electrons and applying high voltage in pulses rather than continuously. So, you can use any method to avoid heat damage here. So, this is how the specimen for scanning electron microscopy are prepared. This completes our section on scanning electron microscopy. Now, like we said, both transmission and scanning electron microscopes are valuable source for a lot of information which cannot be observed otherwise. They have helped in increasing the resolution manifold, so that minute details of different specimens which could range from biological samples to other samples could be imaged. There are a lot of applications of electron microscopy like light microscopy. Like in light microscopy, you have a resolution limit, but that limit has been crossed in or overcome in the electron microscopy. So, various applications are kind of same. You can examine isolated and cultured cells in both transmission electron microscopy and scanning electron microscopy by preparing samples for that. You can examine subcellular fractions by negative scanning or thin sectioning. You can find the precise location and distribution of molecules or cell components to understand physiological function by immunolabeling. This can be done by pre-embedding or post-embedding the through immunogold labeling. So, lot of different things you can visualize proteins, macro proteins, nucleic acids, proteins and nucleic acid interactions, various macromolecular assemblies and likewise. So, it is like you have different applications of electron microscope and it is being used in different areas of biotechnology and even in non-biological fields. Now, I will show you some of the figures here which has been kindly provided by my good friend and colleague Dr. Partha Roy, and I thank you for these figures. Let us see these figures. There are some images here and you can see a lot of these images in books, on internet and likewise. So, this is one figure which has been taken by bright field microscopy, and you can see here clearly the spermatozoa, lumen and epithelium, different sections labeled in here. It is a transverse section of rat testis. So, this is a bright field microscopy. Now, let us see some of these other images. This is again a bright field microscopy of mouse bone marrow stem cells. So, it is a strain morphology and you can see here the particular pattern of mouse cells. The same image has been taken in phase contrast and you can see little without staining you can get lot of details in phase contrast picture also here. This is same bone marrow stem cells of mouse. The same bone marrow stem cells has been done in fluorescence micrography and you can see these cells in here which are fluorescing well and they have been stained in order to with the fluorescent dyes here. This is scanning electron microscope picture which is of a porous surface of a biocompatible scaffold, and all pictures have been provided by Dr. Partha Roy. They have been taken in his lab. So, many thanks to him. All right. So, here we complete our section on the microscopy, and I hope you have understood the basic concepts and details of different microscopy techniques we have discussed in here. We have gone through light microscopy techniques, we have discussed many various basic concepts of microscopy technique. Then we have gone through techniques like bright field, dark field, phase contrast, differential interference contrast, fluorescence, polarization microscopy in light microscopy. Likewise, we have discussed electron microscopy techniques, which are transmission electron microscopy and scanning electron microscopy. Now, I think all of you must have will be benefited by this particular course, and I would suggest you should read more, and this will certainly inculcate curiosity in you. I would say that both microscopy technique, both light and microscopy, and it started with light microscopy, has allowed us to view the tiny world of cells, microorganisms and so on. Now, this tiny world, which is much bigger, maybe much bigger than our world, is like has been made possible, and all the information, all the knowledge which we have gained from this could be utilized for many different application in the field of biotechnology. It like you can apply it for in agriculture sciences, you can apply it in medical sciences, forensic sciences and non-biological sciences also. So, here the microscopy technique has allowed us and has empowered us to understand various phenomena which are going at sub-microscopic level, and to manipulate them and to understand them. This has been a great technique to work with. Now, so this completes our section on microscopy, and now we will move on to the next important technique in biotechnology in this course, that is radioisotope technique. It is a highly sensitive technique and it utilized in various branches of the biotechnology. So, I hope you are understanding all different concepts as we have gone through some lectures, and I hope you will keep listening to these lectures throughout. Thank you very much.